Okay, so good afternoon, and it's my great pleasure to welcome again Dr. Sudipta Hench from Osaka University. He's going to continue his series of seminars. Today, it's a seminar concerning Penrose-Newman tetraspformalism, as I guess. Yes, it's here, and the related optical scalars. So, Sudipta, you can start.
Yeah, so thank you. And it's also my pleasure to present this topic in front of you and discuss the related outcome and future perspective. So today, the talk will mainly based on Newman-Penrose tetrad-formalism and the definition of optical colors, which will be useful in the upcoming lecture to rederive the Hartley-Hawking Tadelating formula. So this work was done in collaboration with Professor Stefano Levaretti and also Professor Vincenzo Vitaliano. Yes, so what is the content of this talk? It is divided into some categories. So first I will talk about the objective of the work, and then Newman-Penrose tetrad formalism in detail and the normalization conditions. And it will be followed by the definitions of the quantities that we use and the Ricci rotation coefficients. Then I'll talk about optical scalars. And next, it will be the conditions for congruence being geodesic. And also the hypersurface orthogonality conditions will be discussed. Optical scalar equation will be the key to rederive the Hartley-Hawking Tadelating formula. So this will be the main goal of today's seminar. So this will be the stage for us to rederive those stuffs and calculate some mathematical formula, which will be helpful in future also. And then I will summarize today's results and also what we can expect from the upcoming lecture. So the main objective is to understand the tadelating phenomenon in the presence of torsion. So torsion is basically when we consider most generic connections, and we can consider that we have most generic connections, and in this case, what will be the modified version of Hartley-Hawking Tadelating formula. So we will get to idea how to rederive this Tadelating formula and also analyze the effect of torsion. So what is Tadelating? Tadelating is the phenomena when we have a compact object, and in the vicinity of that compact object, there is another object, and that object is, so there is a gravitational interaction between them, and so tidal deformation comes into play if they are close enough. Otherwise, there will be change in the geometry. So due to this, how the area of one compact object changes with time, that will be the outcome from Hartley-Hawking Tadelating formula. So if we understand this phenomena in the presence of torsion, then we get to know the imprint of extra degrees of freedom and how it helps to verify some other theory which is not Einstein's GR, or which is natural extension of Einstein GR in the presence of some extra degrees of freedom. So Newman-Penrose tetrad consists of a pair of real null vectors, that is L mu and N mu, and also a pair of complex conjugate null vectors, that is M mu and M mu star, where M mu star is basically complex conjugate of M mu. So we have the normalization conditions as it is written here. So L and M, they are orthogonal. L and M star, they are also orthogonal to each other. N, M, N and M star. So they are all orthogonal to each other. And also they are all null. So the norm of all these legs or all these bases or all these vectors are trivially zero. So that we can see from this expression. And the normalization conditions is only that L and N, if we contract L and N, we get 1, and M star, so we get -1. So these basis vectors form a tetrad, and it can be defined as that this first leg is L mu, and the second leg of tetrad is N mu, third one is M mu, and the fourth one is M star mu. So we have a set of 4 vectors that basically creates the tetrad, which is quite special tetrad, and it is called Newman-Penrose tetrad. And we have seen here the conditions that has to be followed, and also the normalization conditions here. And all these are written in these 3 equations basically. So we also assume that eta is a constant symmetric metric that and the relation between eta and these tetrad legs that is written here. So this constant symmetric metric it takes the form as it is written here in this matrix. So this is kind of analogically, we can think that if we have some other tetrad, then we also had, we also considered that locally the matrix would be flat. That means the local constant symmetric matrix would be, should coincide with the Minkowski metric. So here it is a bit different because the tetrad legs are 2 of them are real and 2 of them are complex conjugate. So it is really specific tetrad that I want to stress. And here Greek indices are for arbitrary coordinate because we are not specifying the coordinate system, at least up to this point. So this Greek indices will be for arbitrary coordinates, and the Latin indices will be for tetrad system. So here A, B, as you can see, it will also vary from 1 to 4. So 1, 2, 3, 4. And these Greek indices, so mu, they are for a coordinate system. So here we have few definitions. So one is the covariant derivative for a generic 4-vector x beta, which can be written as the standard covariant derivative expressions. So here this nabla alpha tilde, it is the covariant derivative with respect to a generic connections. And this generic connection is C beta alpha sigma, where this C gamma alpha beta will have only constant that this connections is the metric compatible. That means the covariant derivative of metric is 0 always. So we are not assuming that there will be any non-zero or non-zero non-metricity, or in other words, that in the non-metricity is 0 always. So the connection is metric compatible. This is our only conditions. And if we consider the connection to be generic one, then we can say, okay, there is a symmetric part and also anti-symmetric part. And usually in Lebesgue connection, we have only the symmetric part. So we do not have any anti-symmetric part. So here we also have anti-symmetric part of the generic connection that is defined as torsion tensor, as it is written here, S alpha beta gamma, which is the anti-symmetric part of this generic connection. Here you see it's like anti-symmetrization bracket. And here we have extracted the antisymmetric part from the generic connection. So S alpha beta gamma is antisymmetric in its first two indices by construction. So here it is written. And the general metric compatible connection can be written as the addition of Lebesgue connection and contortion tensor. So this is generic connection, C gamma alpha beta, and gamma, capital gamma, gamma alpha beta plus K alpha beta gamma. This is gamma is the Lebesgue connection and K alpha beta gamma is contortion tensor. So contortion tensor is basically a special combination of torsion tensor. So contortion tensor is basically antisymmetric contribution to this generic connection, and Lebesgue one is completely symmetric. So any generic connection can be written as this Lebesgue connection plus some contortion tensor. Now we define Ricci rotation coefficients. So this will be necessary to go forward. And we define this Ricci rotation coefficients by this covariant derivative of the basis vector and some contraction as it is written here. And this covariant derivative, nabla mu tilde, is the covariant derivative with respect to generic connection. So if we expand the covariant derivative, and if we open up as a combination of Lebesgue connection plus contortion tensor, then basically we have here this expression. And if we just separate this contortion part and this Lebesgue part, then we have gamma ABC plus K CBA. So this K CBA is completely torsion contribution or contortion contribution. And this gamma ABC is pure or only the contribution coming from the Lebesgue connection. So a full gamma or gamma with respect to the full connection, gamma tilde ABC, can be splitted into gamma with respect to the Lebesgue connection plus K or contortion with respect to the contortion contribution coming from the torsion part. So this is how we can see how torsion affects the definitions of Ricci rotation coefficients, or rather we can say that we can define the Ricci rotation coefficients in terms of torsion in this way. So we have here the quantities that we will use to define some other optical scalars. Basically, optical scalars are the combinations of gamma, sometimes also some specific combinations of gamma. So which we'll see here. So optical scalars in a torsion full scenario, that means we have torsion present. So in this case, rho tilde, which can be written as gamma tilde 1, 3, 4. So here the three indices of gamma, if we choose 1, 3, and 4, then we get the specific combinations of the contraction and this covariant derivative. And also we can define accordingly this epsilon tilde, sigma tilde, kappa tilde, tau tilde, alpha tilde, beta tilde, and xi tilde. So they can all be defined as some combinations of gamma, and they are all with respect to a full connection or with respect to the generic connection. So here we have Lebesgue contribution as well as the torsion contribution hidden inside this tilde, or hidden inside this gamma tilde term. So now we can do one thing. We can now expand this gamma tilde and split each optical scalars into Lebesgue contribution plus some torsion contribution. So in this way, it will be helpful for us to see explicitly the contribution coming from the Levi-Civita part and the contribution coming from the contortion or torsion contribution. So if we do that, then for example, we can split this rho tilde as rho plus rho t. So here rho is pure Levi-Civita contribution and rho t is the contribution coming from the torsion. So if we do that and if we split the term of previous slides, then we can basically write this rho as pure Levi-Civita contribution, where this nabla nu is the covariant derivative with respect to Levi-Civita connection. And rho t is here, as you can see, this is contorsion contracted with the basis vector. So this is pure torsion contribution. So rho t, epsilon t, sigma t, kappa t, they will all be zero if there is no torsion. So rho, epsilon, sigma, and this kappa, they are all dependent on the Levi-Civita connection, and they have no relation or they have no dependence on the torsion. So we can say that these are the optical scalars, which we know that the contribution from where the contribution is coming from. So if we have in this form, there will be no terms misleading, or it will be quite clear when we go forward. So now, what is the conditions for the congruence being geodesic? So for instance, if we have a bunch of congruence, let's say we have a time-like congruence, and then we say, okay, this is, for instance, we have a velocity field. So we can define the velocity field along the tangent of the congruence, or along the tangent of the direction of flow. In this case, if u is the tangent along the direction of flow, along the tangent of along the direction of flow, then we can basically say, okay, u can be considered as geodesic if we have the covariant derivative of u along the direction of u is 0. Then we can say, okay, u is geodesic. Also, if it is not exactly 0, if the right hand side is proportional to u again, then we can say, okay, it is geodesic, but it is not affinely parametrized. So here we will see how this can be defined in the presence of torsion and what is the conditions. So yeah, we can calculate the first order change in the basis vector EA under an infinitesimal displacement xi, which can be defined as this. So here it is the change of the basis vector EA, and this is the infinitesimal displacement. So we get eventually this expression, which I'm not going into detail, but we have this expression. Then we can write that here it is delta L mu 1. So it's this is the change in L mu per unit displacement along the direction of the first basis vector, that is L mu itself. So if L mu has to form a geodesic congruence, then the covariant derivative of L mu along L mu, it should be 0 if they are affinely parameterized. So we get this relation delta L mu as this epsilon plus epsilon star, where epsilon star is the complex conjugate of epsilon, and epsilon is an optical scalar, as we have already defined, and then multiplied with L mu plus epsilon t star, where epsilon t is the optical scalar, the contribution coming from torsion, and epsilon t star is just the complex conjugate of that epsilon t. And here minus kappa m mu star, kappa star. So kappa is also optical scalar, and here kappa t and kappa t star. So if L mu vectors form a geodesic of congruence, form a congruence of geodesic, then both the conditions that this kappa and kappa t should be 0. So how this is how they should be 0? So we can see from this expression that if the derivative or the covariant derivative of L mu along L mu should be proportional to L mu, then we have, okay, so we can write epsilon plus epsilon star plus epsilon t plus epsilon t star multiplied with L mu. So this term is basically proportional to L mu. And we have some other terms. So they should be 0 identically. So kappa should be 0, kappa star should be 0, kappa t should be 0, kappa t star should be 0. So we can set that both the conditions, the kappa is 0 and kappa t star is 0. So if kappa is 0 and kappa t star is 0, then basically these terms, this one, and this one, they will all be 0. And these conditions we are saying, okay, this is geodesic condition. So we can say that L is forming a geodesic if this is true. So kappa and kappa t equal to 0. And if we want that those geodesics are affinely parameterized, then the right hand side of this expression, that should be 0. So we should have this kappa and kappa t equal to 0. And on top of that, we should also have this epsilon plus epsilon star equal to 0 and epsilon t plus epsilon t star equal to 0. So that basically means that epsilon is the real part of epsilon is 0. And here is also real part of epsilon t equal to 0. So epsilon and epsilon t star, they are completely imaginary in other words. So sorry. Yeah. So in GR, this analysis of propagation of tetrad vector along L mu, it can be shown that if they are affinely parameterized, then only if k and real part of epsilon equal to 0, then this is true in GR. Because if we are in GR, then this kappa t star will be 0, kappa t, this term will be 0, this term will be 0, and also this term will be 0. So we will only have this kappa star. So if kappa is 0, so this term will go away, this term will go away, and we also need this to be true. So if epsilon real part of epsilon is 0, or in other words, this epsilon is completely imaginary, then this term will also go away. So in that case, they will be affinely parameterized. If they are not affinely parameterized and we are in GR, so we can leave these conditions as it is. So epsilon should not be completely imaginary, but we need that this kappa to be 0. So we now have the idea how we can see if the congruence is geodesic or not, or on top of that, if they are affinely parameterized or not in the presence of torsion. And now it is really important to see if this congruence can be hypersurface orthogonal congruence. So what does it mean by hypersurface orthogonal? So if we have a congruence, and then if those if the tangent vector along the direction of flow is can be written as gradient of phi, where this phi represents a surface which is really orthogonal to the direction of flow, then we can say that those vectors are hypersurface orthogonal. Or in other words, if we have if we have normal vector of a hypersurface, and that is really parallel to the direction of flow, then we can say the congruence that we are considering, that they are hypersurface orthogonal. So what is the conditions for being hypersurface orthogonal? So if we have a vector field, let's say chi alpha, then this chi alpha basically satisfies these equations or these expressions as it is written here. And this is only the conditions if there is torsion. So as you can see here, S and these terms. So S is basically torsion tensor. So if there is no torsion, if we switch off the torsion, then this right-hand side will be 0. So this is the conditions for a congruence being hypersurface orthogonal. So if there is torsion, then it is equal to the terms in the right-hand side. If there is no torsion, so it will be 0 on the right-hand side. So which can be clearly seen from the expression. And in a torsionful case, if we have, let's say, covariant derivative, then if we can define this covariant derivative in this way, actually we can get this expression from the definitions of Ricci rotation coefficients. Then basically we can find these expressions containing this L, this is the square bracket, lambda and nabla tilde mu, L mu, and this is the end of square bracket. So we can get this expression from the definitions of Ricci rotation coefficients. And this rho star, rho t star, they are all predefined as optical scalars. So if L has to form a congruence which is a hypersurface orthogonal, then actually we can see from this expression that it has to satisfy this, or it has to be, I mean, the right-hand side of this equation, it has to be equal to this. So let's say we have no torsion. So in this case, the second term, basically this rho t star, they will be 0, because this is the contribution coming from torsion directly, and there is no other torsion contribution. So this will be 0. And we have also seen that in the absence of torsion, the right-hand side of this expression should be 0. So if we compare this this expression with this expression, so basically in this case, it will be, as you can see here, in the Riemannian case, that is basically in GR, the conditions for L alpha to be tangent to a hypersurface orthogonal congruence, we can get from this equation. Basically, this is 0 equal to rho minus rho star, and here we have some combinations of basis vector. So we can see from this expression that this rho equal to rho star, which has to be true in order to be L to be the tangent to a hypersurface orthogonal in the absence of torsion. So we can write this optical scalar rho as the combinations of expansion and twist. So this is basically written as minus theta plus I omega, where theta is the expansion parameter and omega is the twist. So if rho is real, here, I mean, rho equal to rho star, that basically means that rho is real. So in the absence of torsion, the congruence is hypersurface orthogonal only if rho equal to rho star. That means rho equal to real. So if rho is real, then this omega equal to 0 because it is real and there is no imaginary part. So which means that the congruence is irrotational or there is no twist at all. So the bottom line is that in the absence of torsion, the hypersurface orthogonality conditions lies on the fact that this rho has to be real. And if we have torsion, so what will be the case? So let's look at that. So let's say we have switched on the torsion, and we can check, okay, if rho equal to rho star still holds. So we can write this expression of hypersurface orthogonality. So with in the presence of torsion, and we can, so basically we are equating this equal to this, because they has to satisfy. And if we just proceed, then if we follow the calculations and we just neglect, or we just cancel 1/3 factorial from both sides. And if we now multiply both sides with this m star mu, m nu, n lambda, and then we use the normalization conditions for tetrad, then we basically proceed in this direction and get this, we plug this normalization conditions equal to -1, 1, -1, and 1. And at the end, we get this expression. So rho minus rho star equal to this torsion term minus this rho t star. So we now will have to see if rho is still equal to rho star, or there is some other conditions for the congruence to be hypersurface orthogonal in the presence of torsion. So here we want to be sure that this rho equal to rho star, if we can consider this in the presence of torsion or not. So just to emphasize this, that this is some, or it can be mistaken if we do not carefully follow it. So rho equal to rho star is true in the absence of torsion. So let's see if it is also true in the presence of torsion. So if it is true, then rho equal to rho star should be 0. So this term should be equal to rho t star, rho t minus rho t star. So let's calculate rho t minus rho t star and see if it can cancel this term or not. So we can, from the definitions of rho t and rho t star, we can calculate and we can proceed these steps, and we get this term. So which is exactly the opposite of, or which is basically adding with this term, not cancelling, because here this we have used the antisymmetric property of torsion tensor, and then it end up with this term. So rho minus rho star is no longer 0 in a torsion proof case. So we can see clearly that in a torsion proof case, for the for hypersurface orthogonality congruence, rho equal to rho star is no longer true, and we have some conditions that rho minus rho star should be equal to this. So it confirms that hypersurface orthogonality of congruence of geodesic does not guarantee a vanishing twist in the presence of torsion. So if there is torsion, so rho equal to rho is not equal to rho star, that means the imaginary part of rho has not to vanish. So we cannot guarantee that the twist will vanish in this case. So there might be twist, or in other way, yeah, there will be twist in a more stronger statement in the presence of torsion. So we can expect some modifications due to this property in the Hartley-Hawking area formula. So let us now set the stage for optical scalar equation, and then once we have this optical scalar equation, we can derive those Hartley-Hawking tidal heating formula from this. This will take a bit, but for today we will just arrive to the equation that we need to go further. So optical scalar equations we can write in this way. This basically comes after playing with Ricci identity. So it will it is very long and it will exhaust too much time. So I skipped that calculation. And here we can see that all these terms that are already predefined, these optical scalars, and whatever is not defined, it is defined here. So alpha t is the torsion contribution coming to the alpha optical scalar, beta, yeah, this is the same. And pi, sorry, I should pi tilde. So this is pi and pi t. And this phi 00 is basically Ricci tensor contracted twice with L basis vector. And we have here theta, capital theta 00, that is written here. So if we now manipulate these equations and try to get all the terms in a way, in such a way that we can see the torsion contribution quite separately. Here, the torsion contribution is hidden inside this tilde terms. So let us try to calculate and see if we can really split the equations in a torsionless terms and also as an addition or another addition of torsionful terms. So if the congruence is geodesic, then this kappa equal to 0, kappa t equal to 0. So let's plug that, and then it simplifies to this. And then we just separate this row, or we just split this row tilde terms into rho and rho t. So if we plug this, and then if we proceed further, so if we plug all the optical parameters here in a fashion that can be seen as torsion plus non-torsion contribution. So if we just do all the steps and then arrive here this equation. So basically we have rho square, rho epsilon stars, and these t subscript t terms, they are contribution coming from the torsion. This is pure Levi-Civita contribution. There's no contribution coming from the torsion. And this is phi 00 is basically Ricci contracted twice with the basis vector, as we already had. So we have these equations, and that will be, sorry. So that will be the basis or the starting point to calculate the Hartley-Locking tire-dilating formula. So we have this optical scalar equations, as you can see here. And so we can clearly identify the contribution coming from the non-torsion terms and the torsion contribution. There are also some mixed terms. So we'll start from these equations in next seminar and try to rederive the Hartley-Locking tire-dilating formula and see if there will be any modifications, because as per expectation that there must be some twist terms, because we already have seen that in the presence of torsion, the twist has not to be vanish if there is even for hypersurface orthogonal congruence. So this is the this was the main goal of today's seminar. And what is a summary of this whole idea is that Newman-Penrose tetrad formalism for most generic connection is discussed. So yes, we have discussed Newman-Penrose tetrad formalism for most generic connection. So we have quite generic connection that can be written as Levi-Civita plus some torsion contortion term. And also we discussed this geodesic and hypersurface orthogonality conditions, both in torsion and torsionless condition cases. So now we have all machinery to rederive the Hartley-Locking tire-dilating formula, and this will be derived for most general connections, but we will approximate at the end to get some simplified results, because as you can see that this equation is a bit tedious and quite complicated in terms of the weightage of terms. So we now have the equations that we need to proceed. And the other is that what we will get from these equations, or what we can derive from this equation, that is Hartley-Hawking tidal formula. And what we can get from that formula, we can get to know the, or how the excitation is released by a black hole in expanding or shrinking the horizon area, or in other words, if we have some flux or ingoing flux that we can consider as a perturbation, so which is basically exciting the horizon, and there will definitely be some shear and twist. So how these shear and twist will be released and the horizon excitation will be relaxed, that can be understood by this Hartley-Hawking tidal formula. So the main goal of this project is to find if there will be any corrections due to the presence of an extra degrees of freedom, that is torsion here, and how this will affect our understanding of thermodynamics, or in other way, that if this will affect the second law of black hole thermodynamics at all or not. So this is also a question for now. So these are the references that I have used. So mostly the Chandrasekhar book, that is one of the pioneering book in this field, and also the other articles, and also the main article that I should have mentioned. Okay, no, I leave it for next seminar. That's the article by James Beetle and Stephen Hawking. So these are the references, and thanks for your attention.